Hi, so this is the continuation of our previous lecture on photolithography. Okay, so I had mentioned that we use silicon wafers for photolithography, and also we talked about photoresist. So here are two images. So the first one shows the silicon wafer. This thin circular object is your silicon wafer, and someone is placing it on top of a vacuum chuck, which is basically the vacuum holder of your spin coater. And after that, in the second image, you see that there is a photoresist that is being poured on top of it. And this resist, as you can see, has a reasonably high viscosity. You can also get lower viscosities. So this resist, now after pouring it, then I will spin coat it at whatever X RPM, let's say 3000 RPM, and then I will get a certain film thickness. Now these films are actually highly reproducible, the same thicknesses you can get no matter how many times you perform this operation. So what happens is, I will pour, let's say, 2 milliliter of the resist. I can sometimes end up pouring 2.5. So is it just the quantity of the resist that you pour? The answer is no. Irrespective of the quantity, of course, you should not pour too much because then you're wasting the material. But irrespective of the quantity of the resist that you pour, you will get the same film thickness because any extra resist will be like thrown away due to centrifugal force. So when you are spin coating, then the combination of a certain resist viscosity and the rotations per minute will always give you the same film thickness, and this is a highly reproducible fabrication method. Okay, now here we are going to, in this lecture, we are going to talk about some fundamental definitions that you need to know when you're performing photolithography operations. Actually, any other lithographic operations as well. We'll talk about them. Okay, so the first one is cross-linking. I said that when you use a negative tone photoresist, then what happens when it is exposed to the UV light? It gets cross-linked, or at least the cross-linking process starts, and then when you do the post-exposure bake, your cross-linking process initiates. So how does that happen? What is cross-linking in the first place? Okay, so think about a polymer chain. So here, so you think about this chain-like molecules. Now these chain-like molecules, what if they had some sort of functional groups on their sides? So long chains, but on the sides they have certain functional groups. Functional groups, what are functional groups? Means something that can react, something that can perform a certain function. So these groups, now in the case of most of the phenol formaldehyde resins, SU8, the resin which we were talking about, which gives us reasonable carbon, these groups can be epoxy groups. Epoxy groups are like these triangular groups with 2 oxygens in the corner, and the third one is attached to your parent atom or molecule. Okay. Now these epoxy groups, when there is a UV light over it, epoxy groups can be actually opened with relatively less energy, relatively lower activation energy. So you have these epoxy groups. Now in these photoresists, the commercial ones, because they are very highly optimized for the lithographic processes. So what they also have, they contain something known as photoinitiators. So photoinitiators are certain materials which are very sensitive to the UV light, and that is number one. And number two, when they absorb the light of a certain wavelength, they undergo certain chemical reaction which would release, let's say, a proton. That proton will then hit your epoxy bond, open it. There in that reaction, another proton is generated. And so this is how this chain reaction then continues. And because of these, now that is how your epoxy bonds will continue to open. These were in the sides of your molecule, polymer molecule. Now, when this epoxy bond opens, what happens is now where the epoxy open, there you have a functional group or something that is a radical. Radical means it has an unpaired electron. It can form a bond. So now it will form a bond with whom? Now it will form a bond with its neighboring radical. So that is how this sideways these chains will start to connect, and your overall material will mostly get solidified because it now has this also side chains that are linked. So in this image you can see that you will have the same kind of polymer molecule, but now the side chains are also linked to each other. So this process is known as cross-linking. Now this, what we talked about, is in the case of UV sensitive materials, but you also can have thermal cross-linking. In many cases, it depends on the bond, it depends on the chemical nature of the material. If it is possible to perform the cross-linking just by providing certain heat, that is in fact done for a lot of polymers. But in the case of lithography, you are more specifically using because you need to use the UV light in a very controlled fashion. And that is why there you have photoinitiators mixed into your material, and then the entire process is optimized. Okay, what else is important for performing lithography? So if I give you a certain resist and I say you need to make a film which is 5 micrometer, will it be possible to always do it? The answer is no. There are certain, if the viscosity of your resist is too high, then no matter how, even at 10,000 RPM, you might not be able to get a film that is extremely thin. So in that case, so basically this is very, common sense, that the viscosity of your resist becomes very important. And in fact, these resists, the commercial resists, they are available in very well-defined viscosities, and you have then also a set of parameters is given to you that, okay, this particular resist at 3000 RPM will give you this, this film thickness. And so at different RPMs, it will give you different thicknesses, but every resist may not be able to always give you, it will have a range. It may not be able to give you thinner than a certain thickness, and also not thicker. So every resist will have its range of operation. So the viscosity becomes very important. In that case, in the case of phenol formaldehyde resins, it's relatively easy to control the viscosity, because you can keep on changing the ratio of phenol and formaldehyde. So if you remember, we learned that phenol formaldehyde resins are of two types, Resol and Novalac. And it's the Novalac ones that are in the liquid form at standard room temperature pressure. And the Resol is in the solid form. So these are all typically the Novalac type resins. Okay. Now, one more interesting thing is that typically the positive resists, they have lower viscosity, and they are used for making, and that's why they are used for making thin films. So they are typically used as what is known as a sacrificial material. They are also relatively inexpensive. They utilize very common chemicals for their developing process. So these positive resists also do not carbonize very well, or they do not yield very high quality carbon. So for our purposes, we will rather use the negative tone photoresist for the carbonization purposes. But generally in the IC industry also, whenever you're using positive resist, then you're using them for making thinner films when you want to make higher structures. And why would you want to make higher structures? For example, when you are making MEMS devices, or you're making microelectrodes, or you're making any of the, if you're making electrodes, what you need high surface area. So the higher the structure, the more surface area you can attain. So in that case, you might want to, so your surface area becomes more important to you. So you want to make higher structures. Also in several MEMS devices, you might want to use higher surface area, or MEMS devices sometimes also, you may have suspended structures, cantilever-like structures. So in that case, you may have to etch away certain layers. You may have to make certain sacrificial layers, complicated structures. So there you will rather go for the negative resist. And our negative resist also carbonize better. So for us, mostly it is going to be negative resist processing. Okay. Now, one more important definition, which is not just for photolithography, it is a general definition for all microscale devices, is the critical dimension. So for all microfabrication techniques, so critical dimension is the smallest feature size that you can reproducibly make using any fabrication technique. Then that is the critical dimension of that fabrication technique. So you will say the critical dimension of my photolithography technique is whatever, 5 micrometer. Now that will depend on what photoresist you're using, whatever is your process. So it's not just a critical dimension of lithography in general, but of your certain process. Now in some cases also, given a combination of a particular resist and an equipment. Let's say I design a 3D printer, nanoscale 3D printer, which only works with a certain type of ink or certain type of resist. In that case, using the combination of this resist and my instrument, then I can say this is the overall critical dimension of the process that can be performed using this particular equipment. Okay. So, what else? Now, all of this process is performed, all nano micro fabrication processes are typically performed in specialized rooms that are called clean rooms. Why are they called clean rooms? Because not just that they are clean physically, but the fact that the air which is there, that is very clean. And it's not just clean, but we have a very specific definition for it. This is the facility which contains multiple filters, and it ensures that any particles that are larger than 0.5 micrometer in diameter, they are, you minimize the number of such particles. Now, why do we do that? Because what we are making here is of only a few micrometer in size. So let's say if you had a particle which is 10 micrometer in dimensions or 20 micrometer, but the structure that you're making, that itself is 20 micrometer. So that one particle, if it drops onto your, or somehow your resist catches that particle, it falls onto your resist, that will look like, big mountain on that little structure, because your overall structure is pretty much the same size as that dust particle. So you want to ensure that particles that are smaller, that are bigger than 0.5 micrometer are absent in that room. So this is a very small dimension. Remember that human hair, the diameter of human hair is also approximately 70 micrometers. It depends on what kind of hair. But 70 to 100 micrometers is the diameter of a human hair. Which means you think about, how small are the things that you're talking about. So you cannot afford to have dust particles and larger particles inside the clean room. What is also important is that the biggest source of contamination in a clean room is actually the human beings. In fact, the very sophisticated clean rooms that in the companies where you're fabricating the chips for your computer, in that case they are fully automated. So humans are not allowed inside. So humans are the ones who cause contamination, change the humidity, by breathing and things like that. So you have to completely gown up when you go inside the clean room and so on. Clean rooms are these facilities, however, where you perform micro and nano fabrication. Okay. Now, clean rooms are also divided into different classes, and these classes, then you can imagine these are based on the number of particles per cubic area. It's measured in feet. So per cubic feet, whatever is the number of particles, depending on that. So if you have class 1 clean room, that would mean that you have one particle, not more than one particle of which is higher than, which is bigger than 0.5 micrometer in 1 cubic foot. And similarly, the class 10 clean room, class 1000 and class, so you have these different classes, 10, 100,000 and so on. Okay. For most of the research purposes, you would use, let's say, 1,000 class clean room. 100 is used, but it's used only in very sophisticated industrial facilities. But also some research institutes do have, we have it here, in fact, also in IIT Mandi, a class 100 clean room, but that is also used only for extremely important applications when we are dealing with very, very, very small feature sizes, and not for general, photolithography learning purposes, for example. Okay, so yeah, and one more important thing is that you need to perform this entire operation when there is no UV light. That is common sense also, because if you're using, your material is photosensitive, so you want to make sure that you store your chemicals also in a UV-free area, and whatever operations you perform, you will, and that is why, these two images that I had shown you before, they look yellow, because this yellow light is what you will have when the light is UV-free. So these are also commonly students would call it yellow rooms. I used to call it yellow rooms when I was performing these things during my PhD. So these are the UV-free lights and UV-free rooms where you perform the entire operation. Here is an image of somebody performing, some experiment inside a clean room. Now I show this image to you because I want to tell you how, when you gown up, you need to really completely cover yourself. Also in this particular case, this guy is not wearing goggles because he was looking into a microscope, but you also wear goggles. So basically you want to completely cover yourself so that you don't contaminate the clean room and you do not, this is the point. It is you are the source of contamination. So this is about the clean rooms, and these are the places where you perform photolithography. Now the question is, are there also other techniques other than photolithography where you can get these structures which can be converted into carbon? So the answer is yes, because we have we have these certain photoresists that can be converted into carbon. Now these these resists you can also perform other types of lithographic operations. Okay, so one important very well known lithographic technique, in fact this is the one that was used before photolithography even, that is known as the X-ray lithography. So you can imagine that what are we doing here? Rather than using the UV light, we are using the X-rays. Rest remains the same. What will change? So if you think about it, spin coating remains the same. What is the baking also? That depends on the chemical that you're using. So the baking process and all that remains the same. Let's say the resist that you have that is sensitive to the X-rays now instead of the UV light. But anyway, everything is, a lot of things are sensitive to X-rays, right? So X-rays are more higher energy electromagnetic radiations. Okay. Now what will be very important is the exposure step. Because you know that how will you make the mask? If you make the mask using any general black ink or even a material, even a metal, a lot of metals allow the X-rays to pass through. So what you need to do is you need to make a mask using a metal which blocks the X-rays. Only then you will be able to mask that part of your resist from the X-rays. Okay, so that is the part that changes. The rest remains the same. However, one thing is that with X-rays, because you can really, X-rays have they go through the material without any diffraction, straight down, and they can actually degrade very, very thick films also. They can go down because UV lithography has its limitation. After let's say 150 micrometer thick structures, then the thicker structures will have more diffraction of light and you may not be able to cross-link them completely. Even 150 is not easy when you're experimentally doing these operations. You need to be really careful. Even that is too thick for UV lithography. And also that is why the structures that are fabricated using photolithography, they are called not 3D structures but 2.5D structures. Why 2.5 and not 2D? Because 2D structures look like this first image. So when you, let's say, perform a lithography with a positive resist, so thin film based structures, thin films are known as 2D. So these kind of structures which are they are thinner compared to their height, they are they are not too thick. Those are called 2D structures. Now you have something in the middle. You have a certain height, but you are not able to create structures in the Z direction. So you have you are able to just increase the size, increase the height of your 2D structure. That much control you have in the third dimension, but not more than that. You cannot pattern anything in 3D. These kind of structures are known as 2D structures. 3D structures would look something like this, which is these are the kind of structures. If you want to make them in resist, these are the structures that you can make using X-ray lithography because of the fact that X-rays are very high energy radiations, and then they do not, because of their wavelength, they do not have much diffraction. So you can get really clean walls and really tall structures. Tall is high aspect ratio structures using X-ray lithography. So this is the advantage, definitely. Now one more thing that I have written here is silicon substrate and the conductive substrate. You can also perform X-ray lithography on silicon. There's no rule, nothing against that. But what we can also, there is something else. We want to make a mold out of this structure, a master mold, and that is why we need conductive substrate. So how do we make that master mold? Okay. Now, yeah, so these are the metals that we use for making, so gold and lead, these are the kind of metals that we use for making the mask, okay. Now, the mold fabrication, why is it done? X-rays are very expensive, and X-ray lithography process is also relatively expensive also because you do not have these facilities everywhere. And also there are, so number one, X-ray generation facilities are not available everywhere, and also it requires a lot of safety features and so on. Also the masks are very expensive. That also makes this technique, in fact, one of the biggest, the factors that adds to the cost. That is the cost of the mask in the case. So altogether, X-ray lithography is very expensive. However, you can make very beautiful structures, really tall, beautiful straight lines. In the case of photolithography, the moment you go for higher aspect ratio structures, you need really good experimental hand to perform those experiments. Otherwise, you will get either T-topping, or sometimes the structures are like this. So this is a problem there. Okay. Now what I can do is, if I need a very high aspect ratio structure for certain applications, so what I can do is I can make just one structure using X-ray lithography. Now this very expensive structure, I can use it as a mold, for making a mold. I can use it as a negative structure for making a mold, and then I can use that mold to make my other structure. So only for making the master mold, I can use X-ray lithography. Okay. So for that, what do I do? I make this resist structure. And I do electroplating on top of that. You know what is electroplating. Electroplating is a very well-known technique where you have this, you make an electrode out of your structure. And then you have a very specialized solution of an electrolyte, which would deposit certain type of metal atom by atom. So then when it is atom by atom, and it is an electrolyte, liquid electrolyte, then that means it can go inside these deep walls. Remember, these walls are still just a couple of micrometers, and then they have very high aspect ratio. So now if you have, however, the conductive substrate, then it will attract these atoms of the metal, and then you will atomically have this layer deposited of the metal, and then finally you will get a mold which looks like this. You will have an electroplated metal, nickel for example. So you can then make, if you remove the resist, and resist removal is not that difficult. You know that you can do it using a developer solution. And if it is cross-linked also, there are certain chemicals which can still dissolve the entire polymer, so it's easier to dissolve it. So now you get rid of your polymer, and now what you have is a mold, negative structure of what you prepared before. Okay. Now this mold can be used for making the same structure in the other polymer. Just press it, and then that's how you make it. This entire process where you first do the X-ray lithography, then you perform electroplating, and then you use that mold for making further structures. This entire process is known as X-ray Liga. And this Liga comes from lithography Galvanoformung, Abformung. So Galvanoformung and Abformung, these are German words, lithography also. So this technique was developed at IMT, in Karlsruhe Institute of Technology in Germany, in the 1980s, and this is a German term that is used for this kind of technique, X-ray Liga. Now, if you think of just the Liga part, lithography, and then Galvanoformung means electroplating, Abformung means molding, and making something using the mold. So these kind of things you can also use with the UV structure, or photolithographically patterned structures. So then what would you call it? You would call it UV Liga. But UV Liga is not used very much because it's already a reasonably inexpensive technique. So you might as well just make several structures in a batch fabrication. But X-ray lithography, since it's very expensive, then you only use it for making a master mold, and then you perform the Liga operations. Okay. Now, where do the X-rays come from? So you know that there are several, these cathode ray tubes, and you can have, for medical purposes, you can have different sources of X-rays, but you also have something known as synchrotron facilities. or synchrotron radiation sources. What happens in these synchrotron sources is that you have like a really large facility. You have you construct a building which is circular. Now so you see in this image, the diameter of these facilities can be up to 1 kilometer. Okay, and so you have basically a building constructed, which has this circular building where you have 1 kilometer diameter. And now what you do is you pass electrons through this entire building. So it's not a building, it's a tube basically that goes through that building. And this is a high vacuum tube. And in that tube now you will have electrons accelerating, circulating in that big, huge building. What will happen? What happens when you have charged particles? And then you also have magnets, by the way. So you have a magnetic dipole and then you accelerate a charged particle inside it. What will happen? It loses certain energy. And that energy, in the case of electrons, is in the form of X-rays. So now you will basically have these radial, tangentially coming, the X-rays are coming out tangentially when you have this radial circulation of electrons. Okay. So now at different places, now you make your office there, you make your lab there, at different places, you know that tangentially many X-rays are coming out, and now at different locations, then you make collection sources. So you have this, for example, my office is there, I sit there, then what I have, I put a screen there, I have these beautiful parallel X-rays coming out. If I need it, then I can also filter the wavelengths, or if not, then I can, for lithography purposes, whatever wavelength I need, or if the range of or mixed wavelengths can also work for me, then I can perform my, that is where I put my mask and that is where I perform my lithography operation. Okay, now these synchrotron radiations, now this is a very basic schematic again, they have various other parts of it, and these radiation sources are basically also used for making a lot of particle physics experiments and laser physics experiments and so on. But they are also used for X-ray lithography. Okay, and in case you're interested, or you further you want to do your research in X-ray lithography or anything related to the synchrotrons, there are two synchrotron facilities in India known as Indus 1 and Indus 2. They're in Indore in Raja Ramanna Center for Advanced Technology. Okay, coming to the next type of lithography, nano imprint lithography. So we were talking till now about micro scale structures, and what we can also do is we can make nano scale structures. Now you know that anyway, when you convert carbon structures, they shrink and then they convert from micro to nano. If you already have a nanoscale structure, then you can even get very, very, small structures. Nanoscale structures will remain in nanoscale. After a certain point, then your material densifies so much that you cannot really shrink it any further when the structures are extremely small. But still, you can, if you make, let's say, a 10 nanometer structure and your, carbon yield is 30%, then you can get a 3 nanometer structure out of it. If it is completely, it can be translated in that scale. So you can get very small structures, but how do we perform lithography at nanoscale? So there are various techniques. One of them is known as the nano imprint lithography, and a variation of that is also known as hot embossing. Okay. So what are these techniques? Now you in this case also have a resist, so you will do the spin coating. That much remains. So you have a thin film of photoresist that you work with. And now, however, rather than using a mask and exposing it through the light, what you do is you have a stamp. So your material should be in a liquid-like state. Here you will not, pre-bake it to convert it into a solid resist film. What you will have is you will rather have a resist film which is not too solidified. So it's a semi-solid state, rubbery state, the best case scenario. And then you have a stamp. Now, when you have the stamp inside your resist, then you will perform the cross-linking and then remove the stamp. Now, cross-linking can be performed using the UV light. That depends on the resist. Or can also be performed using just heating. And that is why then it is called hot embossing. So these are kind of sort of the same techniques with slight variations. So here is the schematic. What you have is so you see that the blue color thing is the mold, and then you press it in and then you remove it. However, what happens is, so you see in the third image here, so you will also have some residual resist in the bottom. And what you need to do is you need to get rid of that resist. So what you will do is etching technique. So there is something called plasma etching. I've not discussed that very much in detail. What you have is a very high energy plasma which etches away your material. Etching is like eating up your material. So if you have this high energy plasma, that will remove that very thin layer of the resist. Remember that that thin layer will be uniformly removed from everywhere. So you will also, like here we are making pillars, let's say. So also from top of the pillar you will lose some material, the same thickness that you lose from the bottom, and that is why in the initial geometry you need to factor that in. So you need to have your structure slightly higher than what you want to make, so that when you etch away the material, then you still get the desired height of your structure. So this is basically the idea of nano imprint. Now, the structures can be in the nanoscale using this technique, and that is why it is called nano imprint. And of course, large area patterning is possible. So if you have a big stamp, then on an entire wafer, just with one stamp, you can fabricate the nanoscale structure. So this is also a reasonably inexpensive lithographic technique. Okay. So as I said, the hardening or the cross-linking can be done using both UV light and heating. One important thing also, also in the case of photolithography, one important definition is also that of the glass transition temperature. What is the glass transition temperature of a polymer? This is the temperature below which the material behaves like it behaves like a glass. Above that temperature, it will become liquid. So behaving like a glass means it is solidified, and we say behaves like a glass, not metal or anything else. We say glass because polymers are typically amorphous. So that is why we say this, because they will have this random cross-linking and so on. However, they will be solidified. So below the glass transition temperature, they will behave like these solid glass-like materials, and that is where we want to we also play with this glass transition temperature during lithographic techniques. So in the case of nano imprint lithography, what you do is you heat the material such that it is this rubbery state, so slightly above its glass transition temperature. And then you once you have the stamp in, then you cool it down. Then also it can become hardened. So you don't really need cross-linking altogether. This is then just playing with the glass transition temperature, just heating and cooling. So that also you can do in the case of nano imprint lithography. Okay. So yeah, the different kind of structures can be prepared, and this is a very easy simple technique. But there are of course challenges. For example, when you remove the mold, sometimes your entire structures will come off. So the adhesion of the material that is being fabricated, your polymer. So it should not have a very good adhesion with the mold. If it has, what you can also do is you can make your mold slightly tilted, so they can easily come off, rather than making completely straight walls. So you have to work with these design parameters such that there is minimal damage on the removal of the mold. So you can have these tapered walls. Okay. Now the molds, because they need to be in the nanoscale, so you need very, very precise and nanoscale structures on top of your molds. So these can be then fabricated using X-ray lithography or E-beam lithography or any of these relatively expensive techniques. But the mold is the one that you need for all your experiments, so that needs to be fabricated in the best possible way. Okay. Now hot embossing, as I said, these are two very similar techniques. The only difference is that the hot embossing is used for also for metal. That can be used for a larger variety of the metals that because UV exposure can only be used for something that is UV sensitive, and also when we are playing with the glass transition temperature, that is also more that because for the metals this temperature can be very high, the melting points can be very high. So in those cases you have if you're using these things, then you have you're limited with the materials. But when you're using heating and cooling, in that case you have or you can use melted materials, so you can go to higher temperatures. For example, if I want to use aluminum, so this doesn't have a very high temperature, high melting point. So what I can use is I can heat it to that temperature, and then I can have my stamp inside, and then also then I can cool it down. So the hot embossing is sort of used for more for a variety of materials. Also, hot embossing was reported before the nano imprint lithography. However, the point is that nowadays the equipment that you get, they can perform both. They can perform both NIL and the hot embossing. Okay. So now one more thing is that this is whatever we are talking about till now was batch fabrication technique. So you have a stamp, but the substrate where you have your polymer film, that is a plate, a wafer. It's a flat and rigid substrate. What you can also do, there are variations of these techniques, because this is a, you can do large area patterning. Then what you can also do is what is known as roll to plate. So your mold can be, rather than a stamp, it can be a roll. It can be a this kind of drum-like substrate which rolls onto your polymer film. So that is known as roll to plate nano imprint lithography. Also, you can have what is known as roll to roll, where you have like this newspaper printing kind of continuous manufacturing technique. So you can also have roll to roll nano imprint lithography. So these are the variations, and because it's a large scale print patterning technique, that is why you can use all of these variations. Now there are also some other advanced variations of where you use lasers, and where you also use electric field assisted patterning and so on. So you can read about all of these things. The point is that there have been nano imprint lithography patterned structures that have been converted into glass-like carbon, again using the same technique that that we use for photolithography. There we just need to do the carbonization, put it in the furnace, 900 degrees inert atmosphere. But these kind of structures, when they are converted into carbon, then they become very, very useful, because now, number one, polymer structures were insulating for most cases, but our carbon structures are conductive. So already there, we can already have so many other applications. Now also carbon is very, glassy carbon is very much mechanically stronger compared to the polymer. It has an inert surface, so polymers may degrade over time or corrode over time, but that does not happen. You know how stable our glassy carbon is. So all of these properties which I had discussed with you for the large scale structures, when we were thinking about making the vessel liners using glass-like carbon, or whenever we were making electrodes, large scale electrodes. So those properties are also true for the nanoscale or microscale glass-like carbon. And that is why now, immediately after you convert these structures into carbon, then you can have many other applications which were not possible using the polymers. Okay. Now, some other things about these, the optimization parameters, you can think about it already. You can think of it yourself. The thermal expansion needs to be optimized for both the mold material and also your resist material or metal, whatever you're using. Then the release of gases, there will be, if you are using a polymer, when you heat it or when you cool it, there will be certain bubbles releasing, certain gases releasing. There also, if there is any solvent, then you are getting rid of it at a certain temperature. So then you need to make sure that this does not create bubbles or porosity into your structures. That needs to be optimized. Viscosity, of course, here compared to photolithography, you will have low aspect ratio structures. That means you might want to use lower viscosity resist. And then, of course, the damage that happens because of mold removal. So you want to make an inert mold, and you want to make sure that that there is as little damage as possible when you remove the mold. If you want to read more about hot embossing, here is a book that I have mentioned. This is by Matthias Vorgul. This is on hot embossing. You can, if you're further interested.